So you have a chapter. What was your chapter about? You took notes. You uploaded them. What was your chapter about? I'm going to grade those. I graded all the honors biology stuff. Now I'm going to grade the AP stuff now, this evening and tomorrow evening. It was about ecology. Specifically, what was a big chapter topic? Give me some topics. Give me some topics. Something from the chapter that you read. Yeah. Biodiversity. What else did you see in that chapter that you felt was remarkable? Excellent. Succession. Very important. We are going to see primary succession. We're going to go out. Actually, you want to know when our first field trip was going to be. Our actual first field trip will be tomorrow. We're just going to go outside during class. But you'll get an example. We're going to go look at primary succession, secondary succession. We're not going to be able to see we'll see primary succession, but we'll certainly go look at secondary succession for sure. So primary succession, biodiversity. What else was in that chapter? Energy flow. Very good. Very good. The change in ecosystem changes. I'm going to put triangles, okay? What else? You should be writing this down. So this is a chapter you should have read, and you should be engaging in this now. Yes?
About tropical level.
What is it?
Tropical level.
Tropical level?
Yeah, not like trophic level.
Not trophic, yeah. No problem. This is trophic level. Actually, trophic level is directly related to this, and we are definitely going to finish talking about that this weekend, then we'll go on. Did you read about biogeochemical cycles? Can we take a look at this? Because this is going to be something that you're going to see this word and you're going to freak out on, right? But it's really easy. At least one of these you know already. You learned it in 6th grade, right? Another one of these you've learned at least through honors biology. You learned it. Another one of these is really easy. 2 others are super easy. Like there's just a couple things you have to know, and you're set. And the hardest one has to do with nitrogen. And it's only because there's some chemicals you have to remember, some forms of nitrogen you have to remember. So it says bio, which means what? Life, right? And then it says, what does it say? Geo. What do you think geo means? Good. Earth. And then there's another word that says chemical. So some kind of compound, right? So everybody okay with that idea? Biogeochemical. It sounds like it's a big deal, but really it isn't. Really it isn't. So biogeochemical cycles. And cycles, what does cycles mean? It keeps repeating itself. That's correct. It's a cycle. So to understand biogeochemical cycles, you really have to understand the idea of what the Earth is. And does anybody know where, let's say, the oxygen in the Earth? Do we get any more oxygen than what we started with on the Earth? So if we have the Earth sitting here, I'm not going to draw the continents, but I'm going to draw. Let's say this is spinning here, right? So the Earth is spinning. What's out here? Space. So there's some stuff in space. There's asteroids. There's energies coming from the sun, right? We know we get our energy from the sun. So there's some plasma, but there's not. It's really pretty much empty. Do we agree? Space is empty. So everything we have, everything we have, we have. We're not getting any more. The water we have is all we have. The land we have, that's it. We're not getting any new land, any new water, any new oxygen, any new CO2. How long has the planet been around? Good. Billions and billions. Let's just say about 4 billion years. How long has life been around on the planet? This is a surprising one for me. I would have thought a million years, or I know some people, bless you. By the way, if religiously you think it's 10,000 years or whatever, I'm not getting involved in that. You please feel free. I'm only talking about what science is talking to us about, okay? I don't want to step on anybody's toes. I'm just trying to stick to the theory here. So 4 billion years, theoretically, life's been around for about 3 billion of those years. Earliest forms of it. Everything that life has had for 3 billion years has been on the planet for the most part. Some stuff's come in the form of asteroids hitting, meteors. That's happened. We've lost some to space, some atmosphere gets lost to space. But in general, we have what we have. Does that make sense?
Yes.
So the question then comes in, if that's all we have, and that's all we're going to get, how does life keep going? How do we keep having babies? How do we keep growing trees? Where's all this stuff coming from? Where's all the new stuff come from if we don't get any more raw material? Do you ever ask yourself that?
That's a good question.
Like billions of years we've been around on a planet, life, not we as humans, but life has been here for billions of years, and it's eating and drinking and multiplying, and we got fish and birds and trees and bacteria and fungi. But where's all this stuff coming from? Like every year somebody has a baby, every year there's a new...
People die off.
People, that's right. People do that.
People die and come back.
So people are dying and born. So the answer is that we recycle. The world recycles its materials. We say recycle. It really, we should just call it cycle. Someone turn the or close the door.
So you believe in that, like, when people die, they become something?
Reincarnation?
We're not talking about philosophy or religion, so what I believe is irrelevant. Let me pause this. So, anyways, a cycle. You have to have a cycle. There's no other way. You got to reuse what you had, right? Otherwise, we'd run out. The sun, for instance, it's thought that the sun will run out of fuel in about 3 billion years. How do we know that? Well, because the sun is burning, is burning so much fuel every day. The sun is burning. Everybody understands that, yes? And it's not getting any more fuel. It's not getting any more hydrogen. And it's burning a lot of it every day. So eventually it will run out. We've calculated how much it's burning every day. We know how big it is. So we know how long this thing has to burn. We think about 3 billion years. We don't have to worry about as humans because we'll be long gone. But the point is the sun will run out of fuel. We can calculate it. Here on this planet, everything that happens depends on the sun. All the energy, that's the only thing that's coming from outside the planet, by the way, on a consistent basis, is the sun's energy. So we call this a closed, or maybe a semi-closed system. As far as matter is concerned, everybody knows the difference between matter and energy, right? In general. Mm-hmm. Yes? Matter and energy. Does everybody know the difference? Well, matter is what? Somebody give me a definition of matter. Yeah.
I think that's anything that takes up space.
That's right. Takes up space.
And has noise.
Takes up space and has mass. That's it. If it weighs something, it takes up some space, we call it matter. Now, it's made of atoms and neutrons and protons, and we could talk about measuring it, and yeah, we could spend a whole year on chemistry, right, at least. People have, my nephew's getting his PhD in chemistry, so it's something we could talk about matter and how it changes forever. But that's not the point of the course. The point is that matter takes up space. It's a real neat, nice, you are made of matter, right? Energy, and let's get a working definition of energy, is the stuff necessary for movement. And let's say to do work. Let's say to do work, okay? In order to work, you need energy. Now, everybody can understand that, right? You may not have a really good picture what energy is. Honestly, I didn't until I got into college. And even now, I'm like, I'm not sure. It takes, because it changes, right? You have electrical energy, mechanical energy, you have kinetic energy and potential energy and light energy and heat energy, and there's all kinds of things you can talk about. But the bottom line is energy is the stuff that you need to move. You need energy to get up in the morning and get your work done. If you run out of energy, you're not going to be successful. You're going to die. You're dead, right? So energy is the stuff. Is everybody okay with those two definitions? So the energy is the only thing that we get from outside the earth. This system is closed to everything but energy. We lose heat energy. Heat energy leaves the planet, but we also get heat energy. Does that make sense? Now, that's an important idea. Energy is constantly being in flux. We do lose some mass. We get some. We get a couple meteors all the time. We do lose some mass, but overall, the matter we have is the matter we have. All right. So we have to recycle the matter. We will run out of the sun's energy. We don't have to worry about it. It's not going to happen within anybody's lifetime that's on the planet right now. Eventually, the sun's energy will burn out. The sun will burn out. However, all the energy that we have, most of the energy for life on this planet comes from the sun. That's where all the ability to move comes from. The matter, though, comes from right here. So any gold, oxygen, nitrogen, phosphorus, sulfur, water, all of it is what we have. The water that you're drinking now was peed out by dinosaurs millions of years ago, right? It's the same water that a T-Rex had flowing in its blood. It's the same water that somebody peed out 2 weeks ago and it got recycled and cycled back up, and you drink it. And you might say, I don't drink water, I drink Coke. Well, that's the same water that's in Coke. Those molecules have been around for billions of years, and they're going to stay around for a while longer. And they make up who you are. About a good 70% of who you are, they make up of just about everything you drink that's liquid is that water that keeps recycling. That goes for everything. The carbon that makes you up is the same carbon that made up the dinosaurs, the same carbon that was in a tree 1 million years ago. It's all recycled. It's all cycling over and over and over again. So we got to talk about how those cycles work. See, that's the biogeochemical cycle, the cycle of life and the earth, these cycles that allow matter to keep staying and being around for use for life. Am I making sense to everybody? Is it clear? I don't want to. All right, so when we talk about cycles, the easiest one that you know, and you maybe didn't, based on what your faces were like when I said that the water you drink is the same water you peed out. That whole, oh, that's nasty, I guess you didn't really think about it when you learned in 6th grade the water cycle. Do you remember learning the water cycle? I know, and you went over it again in 9th grade, and now here you are in AP and you're talking about the water cycle. It's the easiest of the cycles. I'm just going to touch on it because I honestly don't see where there's some nuances, but is something to think about. There's some details we're going to go over, but the water cycle itself is pretty easy. There's condensation in the air, right? We call it clouds. It rains. It rains where? Where it's high, usually in the mountains, let's say. It rains or snows where the... What happens as the water rains, it does what? It flows. It flows down in streams and rivers. It also sinks into groundwater. Now, interestingly, groundwater can stay there for a long time, or it can flow into a well. But the water this is called a reservoir. Do you know what a reservoir is? It's a storage area. It's just storage. Reservoir is a big fancy word for storage. All right, so you're storing water. So the water then it'll go into lakes. It'll go into lakes. It'll flow down into streams. Eventually, most of the world's water goes to the lowest point, which is what? The ocean. And we've gone over aquatic ecosystems. We've talked about that, right? So everybody should understand that there's this aquatic ecosystem that has all these different properties. Now, what happens to the water in the ocean as the sun beats down on it? It evaporates. It goes up. Evaporates. Then winds blow that evaporated water back over the land, where it condenses. As it goes up, it gets cooler, condenses. We'll talk more about that later as we talk about weather. And it turns back. Now, of course, you have one other component, which is the trees. Trees are here. And the trees are they suck up water and they transpire. Do you know this word transpire? Transpiration. That's basically tree sweat, right? The water evaporates from the tree and circulates it out. A lot of water comes out that way as well. But that's gas again. So it's constant. Water's constantly going from liquid to gas to solid. As it falls, the water is fresh water. As it lands on the earth, it dissolves salts and becomes kind of minerally. Still fresh water, but it has some minerals in it. Then when it gets down to the ocean, it dissolves even more and mixes with the salt water and becomes salt water. So this is and then of course that evaporates, becomes fresh water again. So as you're sitting here in your city, or you're on the stream in the woods, and you pee in the river, that water goes into the river, into the lake, into the ocean, and the pee gets eaten up by bacteria. The urine gets eaten up by bacteria as part of the nitrogen cycle. All that stuff gets broken down by other living creatures. The water, though, stays in as a solvent. It'll evaporate and continue on with the water cycle for as long as the planet has the sun shining down on it. Are we good? Mm-hmm. That is the water cycle in essence, and we'll talk more about that cycle later when we talk about and we talked about where that water is. Most of the Earth's water is where? In the ocean. 90+% in the ocean. Ocean. It's in the ocean. On the surface of the planet, in the ocean. Actually, some people think that there's a underground ocean now, interestingly. Of the fresh water, that's all salt water though. It's not usable by humans. So there's fresh water. Where's most of the fresh water? Most of the fresh water is in glaciers. It's frozen. So again, not usable, right? It's in the Arctic or the Antarctic. Most of the fresh water on the planet's in Greenland, Antarctica, and the Arctic. Although we're having a lot of melt, and as we go into global climate change, you're going to see that we're losing a lot of that solid water, which has an impact. A lot of impacts, actually. Yeah. So that that water's trapped in glaciers. Another good portion of the water's in lakes. That's the most usable waters in lakes. It's a reservoir. Underground water is accessible with wells, but some of it, or aquifers, some of it becomes not accessible because it actually goes into the rocks. So water that's in a rock is difficult to get out again because rocks actually absorb it, all this water. All right. So understanding that, we have to talk about, when we look at the carbon cycle, so that's one cycle, the water cycle. We can look at another cycle called the carbon cycle. The carbon cycle is based on one idea, all right? And it's an idea that we covered in 9th grade, and it's this, and you've covered in middle school. I know that's kind of one of the first things you learn in K through 8, biology or science. You have an animal, whatever that animal is. What goes into an animal? What does an animal take in? It takes in food, but we're more sophisticated than that. We can break down that idea of food. We're taking in carbohydrates, right? We take in, that's basically food, but we also take in proteins. We take in lipids or fats, all kinds of lipids, and nucleic acids. All these things are forms of carbon. It's kind of a really big deal that you understand that all this stuff that you eat is just carbon in different ways, right? It's just different ways of packaging it. You should hopefully remember that from your freshman biology class.
That's why carbon is so important in like chemistry and all that.
That's right. That's why carbon's arguably the most, well, it's not arguable, I don't think. It's the most important element on the periodic table for life on this planet. So there's carbon. And when so that's what's going into the animal. What else goes into the animal? In order to use this food, this stuff we call food, in order to use it, what do you need to, that's where we're going to get our energy. What do we need? Anybody remember cellular respiration?
Oxygen.
Oxygen. You need oxygen. You need O2. That's what's going in. What comes out of the animal?
Waste.
Well, yeah, I'm going to go ahead and put it down. Waste. So there's waste. There's this word waste. What does that mean to you? That's right. This stuff we can't break down. It's wasted food. The stuff that came in that we can't use. That's why we call it waste. All right? We just can't use it. It's disappointing. It's like when somebody gives you $1,000, you can only use 10 of it. You're like, I got to throw away $990. That's really sad. So you're taking all this food, but you can only use 10% of it. You can only use 10% of all the food you eat. You only use 10% of it. That's just sad. The rest is wasted. Isn't that crazy? 10% of the energy. It also tells you, when you got a fat guy like me, how much I must have been taking in, right? Because if I'm gaining mass, right, and I lose, I can only capture 10% of what I'm eating. Dang, that's a lot more. Now, it's not really that much. It turns out you can add a little bit every day, and as you add, you accumulate, right? So it's compound interest, if you will. So it's really not as simple as all that, but it is interesting. So here's waste. That's one thing. What else comes out of the animal? The one I'm really interested in. Carbon dioxide is right. So out comes this other one that we're really, because this is we're talking about the carbon cycle, that's the one we want to be thinking about, is carbon dioxide. Now we say we're cycling it, and we're putting out carbon. So we take in this food that has all this carbon. Most of that food, at least at some point, started off in plants. Does everybody understand that? Plants are the source of food for animals and bacteria and fungi. It's the actual beginning. So where does the CO2 go? That CO2? In the atmosphere, that's right. It goes in the atmosphere, is correct. We breathe it out. Good. That's right, you got it. Do you remember? Then CO2 goes, the CO2 goes where?
To the plants or plants.
That's right, to the, yeah, exactly. CO2 goes into the plant, and into the leaf specifically. Huh? What do you mean stop? Look, I don't have time to worry about details. You want me to go ahead and draw it neatly? You want me to draw a nice, neat leaf? All right, there you go. It's as good as it's gonna get, all right? Why are you laughing? Why is you laughing?
It's over.
I'm doing the leaf. You want to leave? I get the leaf done. There's your leaf. You happy?
Yep.
Right.
Say you didn't care about it.
You're the one who wanted leaf. You got it. So, anyways, the bottom line is you got a leaf. I wish I could adjust the transparency. Huh? So you have a leaf and it's green because it's not going to be able to use the green part of the spectrum, right? The light that the sun is shining upon us. So now what are you going to do about, as light comes in, it's going to take in the CO2 and make what? It's going to take carbon dioxide. It's going to take in some oxygen. It does use oxygen. Let's remember that. It uses oxygen, but it makes its own oxygen. It takes in what else? What's the other thing it takes in? What do plants use? Come on, guys. To do photosynthesis, what do they use? They use CO2, sunlight, and what? One other thing. Water. That's right. H2O. So you do remember. All right. So water's going in. CO2 goes in. And what plants do with that, with the magic of sunlight, the energy, right? The energy. In order for plants to do work, they need energy. The source of energy is the sun. It's okay. I know. I have a short sleeve shirt. All right. So the plants are going to take that, and through a whole system that we went over in photosynthesis and high school honors biology, you make these foods, right? You start off by making sugar. They start off by making sugar, then they make lipids, and they make proteins. There's a plus here, plus proteins, and they could take all kinds of things and make proteins and nucleic acids. Then come the heterotrophs, the animals, and what do? They eat the food. Right? Even if you're not eating the plant, you're eating the animal that ate the plant, right? That's the whole trophic level idea, that everything starts with the producers. We call these plants producers. And we can add up everything that they produce, all the mass that they make. So these are producers. They're producing something. What are they producing? Sugars, lipids, proteins, obviously more of themselves, right? They're doing it by taking in CO2. So where does that sugar go? Where does it end up? All that sugar, lipids, and everything goes back into the animal, back into food. And what did we just make we just made a cycle. Specifically, it's the carbon cycle. All right, so in the most rudimentary form, there are obviously a lot of things I'm leaving out we'll have to discuss tomorrow. There's a lot of detail. I'm going to give you a handout. You should read your chapter reading. Those people that are new to the room, to the class, I got to give you your books. But the carbon cycle, there's a lot of detail to it, but in essence, it's this. Out goes CO2 from the animal, in goes CO2 into the plant, and it'll cycle forever if you leave it alone. Of course, we don't leave it alone because we're humans. We got to mess with things. But carbon, essentially, the life is producing something. Now, if I was going to look at the world and I was going to ask you, what would be the net? Do you understand this word net before I go on? Do you understand this word net? Like net income? Do you know what net income means? There's a word that says net, N-E-T. What does it mean to you? Net income is about money, that's correct. But net, what do you mean by net income? Why not just say income? What's my income? My income's $1 million a year. Well, great, but I only take home $50 a year. So my net income is what? No, that's gross. So the million is the gross, the net is the 50.
Whatever left after the deduction.
That's right. So the stuff that's left over. Stuff that's left over. Can I leave it like that? Can we just say stuff that's left over and we'll look at the math in a minute? Yeah. All right. Remember, you should have calculators because you're going to need calculators for class. The stuff that's left over. So in the case of your income, who works here? Who goes to work and gets a check? Oh, not a lot of people. Oh, that's interesting. You get a check you get paid, you work 100 hours, you get paid $10 an hour, you expect how much money? You get paid 100 hours, you get paid, let's see if you can do some math, some quick math. You get paid $10 an hour, and you work 100 hours, you busted your butt for 100 hours, and you get $10 an hour, how much money do you expect in that check? $1,000. Ah, but you never get $1,000. They're always taking out something, fees and taxes and whatever. You end up with $600. So that is your net, guys. That's your net income. That's what's left. The stuff that's left over is your net. Okay. Let's take a look at this. Net primary productivity. Somebody want to read in your handout what the first paragraph here, so I don't have to do it? Not that one, the other one.
I don't have to.
Go get it. It's over there. It's the one that says calculating net productivity. It says globe, carbon cycles, 3 pages. The other one's about the ocean. It's very important. You know, we're going to have to talk about the ocean as a primary producer. But let's go ahead and look at calculating net productivity.
To read the first paragraph?
Yes, please.
Depending on your initial research question, you may be interested in the annual carbon uptake at your sample site. This can be determined by calculating net primary productivity, or NPP. In order to calculate NPP, you will need multiple years of biomass and carbon storage data for your sample site.
So why do you need biomass if you want to know what your net primary productivity? Let's go ahead and let's read the background. It's always important to read your background. Somebody want to read it? Somebody else? Okay, let me motivate you. we'll call it participation points, and every time, and from now on, every time you participate, I'll give you 10 points there. Motivation. Yeah, go ahead.
Net primary productivity, or the production of plant biomass, is equal to all of the carbon taken up by the vegetation through photosynthesis, called gross primary production, or GPP, minus the carbon that is lost to respiration.
Okay, so now let's think about this. It's interesting. If you just read it, you'd go home and say, I didn't understand that, and say, Mendoza didn't teach me nothing, and you get all upset. Because I'd give you a quiz, I'd give you a test question, I'd give you the carbon data, and expect you to be able to calculate net primary productivity, and I swear to you, I will hear people say, I didn't know anything about this. So let's take a look at what net primary productivity is. It's first of all, it's the production of plant biomass. What does that word biomass mean? Remember, you want your 10 points a day,
All
so
mass, like all life mass.
it's the mass of plant life. I mean, it's not hard, right? Biomass, but it's because it's plant biomass. There's if you're looking at biomass, you're looking at plant and animal, right? So plant biomass is equal to all the carbon taken up by the vegetation, so all the carbon that the plants take up by photosynthesis. That's called gross. That's that $1,000 check you were expecting. That would be your gross income. Gross means the stuff before they take things out. Are we all good with that idea?
Yeah.
Please know that, because you're going to see gross and net all the time. So gross primary productivity is GPP. NPP is net primary productivity. And this is really easy. If you know this, if you know what the basic, like the building block of the carbon cycle, what is it that we're doing? If you know that plants take up CO2, they build themselves up, and animals use CO2, they eat it. If you know that, then you have some idea that how to calculate the net primary productivity. So if you calculate how much biomass has changed from one year to the next, if you had 100 pounds of plants, and next year you measure, you have 200 pounds of plants, what's your gross primary productivity, your GPP?
Say it one more time.
So you have I'll try to say it a little, maybe I can say it slower. I don't know if I can say it any more clearly. So plant biomass, how much mass you have of plants that's it. That's what plant biomass is how much mass you have of plants, measured in kilograms or grams. If I have a gram of plants, then I have a biomass of 1 gram. That's it. Now, if my primary productivity was, if I start off with 100 kilograms of plants, 1 year, year 1. Year 2, I have 200 kilograms of plants. What's my gross plant, primary productivity? Huh?
100 kilograms?
Right. I said 100, and then going to 200, your gross would be 100 is correct. Right? It's just how much has you changed? How much have you what? How much carbon have you captured? How much carbon have you captured? And we're measuring the mass of the plant, because what's the plant made of? It's made of carbon. It's made of proteins, lipids, sugars, etc. So in terrestrial systems, NPP is often, in terrestrial, this is key. That's why I gave you the aquatic system one, the ocean one. In terrestrial systems, it's calculated by determining how much the annual carbon storage increment, right? Therefore, using biomass, the carbon storage estimates from a sample site, you can calculate above ground NPP, sometimes referred to as ANPP, by taking the difference in carbon storage between years, annual NPP. So you just take carbon stored for year 2, carbon stored for year 1, you measure it or estimate it, and you calculate a number. NPP is one of the most frequently measured ecosystem processes because it's central to the storage and accumulation of carbon in ecosystems, as well as the yield of usable products like lumber, food, etc., like corn, etc. From NPP calculation, you can also calculate annual CO2 uptake from your sample site using instructions at the end of the document. So we're going to do this, we're going to calculate this stuff. And I have some data tables for you to look at how we're going to calculate this. But the bottom line is you have a certain amount of CO2 that's taken up by the plants, that's measured and estimated, or actual mass of plant. That mass of plant that changed from one year to the next, we can measure how much change has occurred in the net. And why do we call it, by the way, why do we call it primary productivity? You guys read the chapter, you know your trophic levels.
Because it's the primary, like, part of the chain, the food chain.
That's right, it's in the producer section. It's the first. Producers are the first. So when we say primary productivity, is the productivity of the first level. Right, the first level. It's the producer level. And so we call it primary productivity because we're looking at how much production of plant material was there for that year. Now, I don't think that, was anybody find any of this difficult?
Not really.
So I can give you a quiz tomorrow and you're going to be okay with understanding this. By the way, for those of you that are new to the course, I'm going to upload this evening. I uploaded all the previous lessons on aquatic ecosystems already. It's on the class webpage. I don't know if you don't know that we have a class webpage, maybe. I guess I should go through that since we have enough. We have like 3 people that are new to the class. Spend a little bit of time doing this. I sent you this. If they register you, it looks like your website looks like that. You go to this one, the APES. There's your pacing guide. So you see that we are on the 26th of August. So we are here. Tomorrow you have a lab on trophic levels. You have a lab report due the next day. And you'll have a case study. Yeah, the case study is going to be due on Thursday, and then you have a quiz this Friday on cycles. That's carbon cycle, nitrogen cycle, all the different cycles. We actually might not do the trophic level lab until later, only because we haven't finished all the cycles yet. I was due to finish those last week, and we didn't. So these are the 3 cycles that we should have finished last week. We've had a lot of moving around and schedule changes. We also didn't do the cycle quiz. You see that? Because Friday it was a crazy day. So there's some stuff to get. There's some stuff we got to get done that we have to talk about. Some positive and negative feedback stuff. And I'm not sure how we're going to be able to catch it up, but we will catch it up. Also, you have Khan Academy to do and AP Classroom to do. So that's the calendar. If we go back and we take a look at APS,
What's that?
it's a water strider. We look at the first marking period, you'll see there's 3 weeks. The first 3 weeks are there. All the content for all 3 weeks are there. Class instructions for the first 3 weeks are here. Literally.
So I just wanna,
3 hours worth of aquatic biomes, and if you don't like that, you don't have time for all that or whatever, you guys can do whatever you want, Khan Academy, but you have to know you will have an exam on aquatic biomes.
Okay.
All right, let me take attendance. I'd like to talk to Ms. Rayford before you leave, please. Over here and individually. Let's take a closer look at this. We look at this triangle, and this is key, is that every level above this producer is going to be only 10%, it's going to have only 10% of the energy that the level below it had. So let's do some simple math. Let's do some simple math. If you had the producers represented 100 units, I don't care what it is, and they can give you all kinds of units. They can give you kilojoules, they can give you biomass, they can tell you there's 100,000 tons of producers, right? What is the amount of energy that's going to be transferred to the primary, secondary, tertiary, quaternary, all the way up to the apex, right? Apex predator. How much energy gets to the third? The tertiary consumer. If you have 100 units at the bottom, how much are you going to get at the top? Here, at the third. Now let's do the math. You get third gets 10% of the second. The second got 10% of the first. The first got 10% of the producers. So what's of me? Times, good. So 100 times 100 times point zero, no, it's 10.1, right? That's for this one. That'll get you the second. That'll get you a second, right? And then you're going to multiply then times another 10%, right? And then you're going to multiply times another 10%, right? So that you can get to the third. This is where drawing this out helps when you're doing a problem. I could see you easily making a mistake and only doing it twice, or making a mistake and doing it 4 or 5 times. If you draw it out, and you say this is 100 units, there's 1, 2, 3 transfers, right? So now I know I got to multiply it 3 times 0.1 3 times, right? That makes sense, yes? So basically you're moving the decimal 1, 2, 3 times. So you don't even need a calculator for this. You move the decimal once, that's 0.1. Twice for another 0.1. And the third for 0.1. So your number is 0.10. That's the energy available on a third trophy club. That's it. If you had 100 units, then you have 0.1 units by the time you get up here to the third. What are units? Kilojoules, whatever. Whatever units they give you in the problem. Are we clear?
Yeah.
It's really easy if you remember that every time you eat, you're only going to take advantage of 10% of that energy. 90% of that is lost. Lost to what? What is it lost to? Where does that 90% go? Heat. You lose it to heat. It's inefficient. The things you waste, the poop.
So you said the energy goes to.
So if you have a plant that has 100 units of energy, the primary consumer can only actually take advantage of 10% of that. The rest is lost to food that they couldn't digest or to heat. It costs you energy to eat, right? You have to capture it, you have to chew it, you have to digest it, you have to absorb it. Then you have to build something with it. So all that energy, you take all that into account, we're lucky to get 10% available for us to do the work we need to do. So it takes a lot to get that energy into you. All right, so again, this is the net. This is the gross, this is the net at each level. You can keep going all the way to the top. It's really easy math if you remember what you're talking about. Up at least a couple ideas here. Well, I guess we should. What do you think happens in net primary productivity throughout the seasons? What do you think happens during the winter to net primary productivity?
It slows down.
It slows down. It slows down a lot. Why does it slow down in the wintertime, based on what we discussed with the planetary movements?
Well, there are so many producers, especially on the young fish, that a lot of plants die and stuff.
They kind of die, but a lot of them survive the winter. And you said what animals do? What are animals doing? Animals hibernating. Would that increase net productivity? Net primary productivity? Would that decrease net primary productivity? That would.
Oh, because they're not.
That would increase net primary productivity because you're respirating less. Remember, you have to remember what is net primary productivity. Net primary productivity is equal to photosynthesis, right? How much energy you're capturing from the sun minus what? Respiration. When animals are hibernating, they're doing what? Less respiring. Even if they're not actually hibernating, even if they're just slowing down in their caves and just resting more, you're still using up less food. You're eating less. So your net primary productivity is going to be greater. In any case, what happens in the seasons? What's happening in winter that would make this number less? Somebody said less. I agreed with them.
There's less sunlight.
Less sunlight. That's all. Less sunlight. And in northern climates, the water is solid. Can plants use solid water? They can't use it. Frozen water is useless to plants.
You said frozen water?
Frozen water is useless. They can't grab it. They can't put it in their mouths and melt it like we can, right? You could eat snow. Plants can't take advantage of snow. They have to sit there. So they have less water available if they're in the far north, but they certainly have less sunlight. Everybody agree there's less sunlight in the winter?
Yeah.
Okay, so that's not true of the tropical areas. Do you remember that? In the equator, near the equator, let's go ahead and draw the Earth again. The Earth is spinning 24 hours a day. How long does it take for the Earth to spin on its axis? 24 hours. As this Earth moves around the sun, as the Earth moves around the sun in an orbit, we know that if the Earth is pointing to the sun, that the north is going to have more sunlight during the summer than it is during the winter. So in order to prove that to you, what I'm going to ask is Mr. Kofi, if you could take the chair that's over back there and pull down the globes and pass them around. Let's keep the lights off. And here's some when you take it down, you're going to see some Post-its. Take those Post-its off it. These are expensive. I mean, they're not expensive individually, but they cost me money. I'd rather not lose any. So when you take them, you ladies back there, grab them as he passes them down. Move the chair over and don't knock anything else down. But you don't have to go all the way up there, just stand on the chair and grab them and pass them down. Pull out a cell phone so you can use the light on your cell phone. I like there to be, I think there's enough to have 8 groups in the class, so we got up to 8 groups. Work with your tables, with the people at your tables. Thank you, Mr. Kofi, for cooperating. If they're deflated a little bit, could you pop it open and inflate it, please? Pull the last one down too, will you? Pull them all down. I'd rather not have them just up there wasting away. There's a big one down there too. You see the big one is clear plastic. If you could pull that down as well, that'd be great. You could have 2 to a table if you need it. You can have your own individual. Looks like we have enough. Take the Post-its off, please. Now, with a partner, Ms. Rayford and I work together. Point the northern area up. So this is the north. Find where you live. Find where you live. Find where you live in America. Yeah, that's it. Lake Erie. And then use your cell phone light.
There's really a lot of water for this.
There is.
How long do you think it take to get here?
It depends on what kind of boat or plane you're using.
No,
So
not
you-
in the water.
In a boat or a raft? What kind of boat? A fast, big boat or a slow
A
sailboat?
Big sailboat.
Sailboat takes months.
Oh,
So when you're turning, when it's turning towards the east, right? So now, I wish we could make it darker in this room, but we can't. Look at how much sunlight. Point it towards the sun. Remember that when you're dealing with the turning, the turning is towards the east, okay? It's at an angle. So the person in the center is the sun. So it's turning like this. It's pointing towards the north. As it goes around, it keeps pointing in the same direction. Don't keep pointing it towards the sun, right? It's still pointing in that angle. Do you see how it's not pointing towards the sun anymore? Did you see that? Here's what some kids do. They'll keep it pointed. They'll turn themselves. That's not what's happening. The earth is going around the sun. The sun stays still. So this angle stays constant. Don't change the angle this way. The turning's happening this way. Right? That's what makes a day. And as the earth goes around the sun, it goes around this way. You see it? Now you see the sun, the north is pointing that way. And keep turning it. As you look and see how much sunlight you get. Imagine there's no light on this side. This would all be black. This is night, right? It doesn't look like it here because unfortunately I can't close these windows. But this would be all black here, all right? So as it keeps turning now, you can tell, right, that would be northern winter, and it would be southern summer. Look at where the north is. North is up here, south is down here, Australia, South America. So play around with it and make sure you understand how this turns and how the seasons would change. Why is it you would get less sunlight in the winter time than in the northern time? I like what you're doing there. If you get the light real close to the sun, right, to the planet, you'll see a little better what the sunlight, what it would look like. So you do. That's right. So now there it is. It's turning. So this is northern summer. Look at how much sunlight you get. Turn it. Keep turning. So that's 1 hour. That's 2 hours. That's 3 hours. That's 4 hours. That's 5 hours. That's 6 hours. 7, 8, 9, 10, 10, 11. Hold on. You went too slow. Too fast. I can't keep up. Each one of these lines is an hour.
oh.
So all right. So now go ahead and turn it. That's 1 hour, that's 2 hours sunlight, 3, 4, 5, 6, 7, 8, 9, 10, stop. Now it's nighttime on the East Coast, it's still daylight out here, see that?
That makes sense why it'd be like this sometimes.
Yes. Keep going, 11, 12, 13, so you got about 13, 14 hours of daylight now, right? Now we're gonna turn it, it's gonna go around the sun, we're gonna pretend like we're gonna pretend like the sun, like we're over here, okay? So that would mean that this will be pointing this way, right? So go ahead and turn it. So there's 1 hour, 2 hours, 3, 4, 5, 6, 7, 8, 9, 9 or 10, less hours, right? Now we're gonna pretend like the earth went all the way to the other side, so it's the other way. It's still pointing that way, right? So the sun is still pointing this way, so. You see that? So the north is only gonna get, let's look at where we are again, let's look at America. Where we are, you see in Alaska, it's 100% dark. There's no sunlight gets to Alaska there. It's because it's northern winter. But if you look at us in Cleveland, you see we get some sunlight, right? So that's 1, 2, 3, 4, 5, 6, 7 or 8 hours, something like that. And then we're in the dark again. So we go from something like near 16 hours a day to like 6 or 7, 8 hours a day, something like that. Why? It's because of the angle that the earth is taking to the sun. So less sunlight in the winter means it's colder, but it also means that there's less primary productivity. Is that making sense to everybody? And that's how the angle, as you play around with it, go ahead and continue playing around with it for the rest of the period, and make sure you understand what net productivity is. Make sure you understand, because that's the next quiz. And you'll see what happens during an eclipse. If you look at what happens during an eclipse, if you have the sun here, hold it right there. So if you have the sun here, and of course this doesn't have anything to do with seasons, but it's a common misunderstanding. If you have the sun sitting here and the moon comes around, it just blacked out the sun. So that's why an eclipse makes it dark, right? And you can see if you're further north, the angle of the sun to the eclipse, it can be different. So you get partial eclipse, a full eclipse, right?
Oh, that's Canada. That's Canada.
That's true. Here, what's interesting to me is South America is not directly underneath. A lot of people think it's here, you just drive straight south. You go straight south from here, you got the Atlantic Ocean. It's actually east of us. That's why it makes it easier for people to go from Africa to South America, see how close it is, compared from Africa to like the United States.
Yeah,
So
it's all the way. So all of this was worn, then it broke apart.
yeah, see, look, you can even see how they fit. You see how this one fits in this, and this kind of goes over here and fits in that. The puzzles seem to fit if you take a look at it.
And it's just a lot.
That's a
It's
clue.
really a lot of water.
What if the world lit up from the
It
inside?
is 70%. Isn't that
How long
crazy?
do you think? How long do you think it to go to every ocean?
Look, it's
How long?
Depends on how you doing.
Like, okay, so from North America to the Atlantic, from
But- So that is, we're going to come back to net primary productivity. So what is it?
Evaporation.
That's right. So we have evaporation. Evaporation from where? Ocean, lakes, runoff. Now, we talked yesterday on Friday about these packets and how we didn't want to put any extra work on you, right? Because you have a lot of AP classes. Isn't that right? Didn't we discuss that?
Yes.
All right. So, somebody came up with the idea that I thought about over the weekend. I thought it made a lot of good sense. Is I'll start using those packets in the notes, so you'll be able to use those as part of your notes as well. Does that seem reasonable? So we'll try to answer the questions and fill them in as we go along as much as we can. And then that should reduce your stress with the amount of work at home. Is that a good compromise to the problem we had at hand? All right. All right, so evaporation. When we're dealing with evaporation, it's the water in the bodies of water start to have liquid water turn into gas, right? And we call that evaporation. Now, evaporation is important because it's important for a lot of reasons, but let's think about it. What's most of the water on the planet? It's salt water, right? So that's salt water. So salt water is not really usable by us. Salt water is not really usable by us. We can't drink it. But what's really cool is that as the water turns into gas, the salt stays. This water is going to be fresh water. So rain is not salt water. Rain is fresh water. So as this water comes up here and forms clouds, by the way, it moves up, and we're going to talk about that soon. As it moves up, what happens to the atmosphere as you move up? It gets cold. I'm glad someone said that. How do you know it gets cold?
Because it's like the atmosphere, the temperature in the air is not, I don't know, describe it.
Yeah. Good. That's a good way of thinking of it. Space is really cold, and the higher up you go, the closer you are to space, the colder you get. Okay, I'll go with that. It has to do with how thin the air is and how heat is transferred, but let's not worry about it. That's good, right? Whatever works to try to get that in our head. Let me lock this up. Oh no. When we're talking about air moving up, as you go up, as this water evaporates and moves up, it's warm. Warm things rise, right? We all know hot air balloons go up. Is that correct? Hot air balloons go up because warm gases are less dense than cold gases. And as water evaporates, it turns into a gas. It goes up. As it cools off, what does it turn into? A cloud. But what is that? It goes from gas to what? As a warm gas cools off, specifically warm water gas cools off, what does it turn into? Liquid. So now we're starting to form little tiny micro droplets. They're not quite raindrops yet. Micro droplets. So clouds are not gas. Clouds are liquid. They're very tiny droplets of liquid, but they're liquid. And they're floating in the air. And what is going to happen is ultimately you're going to get these clouds are going to get pushed by what? Air currents is correct. So these clouds are going to get pushed in this direction. And what do you have in that direction if we're drawing something as part of the water cycle here? Land. I should have drawn it brown or something. But now, those of us that studied our aquatic ecosystems know that there is this area here that's going to be on the quiz, the area near the shore. We know that the area that's a little further out, remember the tidal zones? The quiz tomorrow is on aquatic ecosystems. It's what you have your AP classroom problems on as well. Remember, you have your tidal zones that go up and down. They dry up and then get wet again. You have another zone here, a third zone down here, and then of course you have the bottom. Please try to remember all that. So as you have land, you have these things called what? What are these things here called? Mountains is correct. And what is at the top of a mountain? If it's cold here, how cold do you think it is up here? Real cold, right? So it's very cold. So as this goes up, as this hits the mountain, what's the cloud going to do? It's going to start to condense even more, isn't it? That's right. but it's gonna keep getting pushed. It's gonna push up against the land and move up. Eventually, it'll rain. It'll start falling out. It'll get so dense, it'll fall out of the sky. In either as rain, if it does it down here as rain, or up here as snow. Especially in the winter, because it's colder. Does that make sense? Everybody got that? That's a real part. This is called, what part of the water cycle is this? And that's precipitation. And precipitation is just simply water, something coming out of solution. Gas is in solution. It's in the gas solution called air. And water comes out of that gas solution in the form of liquid. Now, when the air gets on this side of the mountain, do you think it's going to be drier or wetter? Say again? You think it'll be drier? Why?
Because at the top of the mountain, how it's colder, it's probably solidified at this point.
Exactly. So you got all, this is precipitating all along this path here, all up and down this path, you have precipitation. It's all precipitating. All the water that's in the air is falling out. When you get to the other side, what you expect is the air is going to be a lot drier. The air is a lot drier. And in fact, that's what happens. We call this the rain shadow effect. What happens is when you have mountains near an ocean, for instance in California, and I saw this, I have pictures of it on my phone, I can show you later. I went to the mountains of California, I climbed them this summer, and I went to the highest mountain near San Diego, and I looked, I saw the ocean where I was, the Pacific Ocean, and I looked down and there was a forest, it felt like Yogi Bear was going to pop out any minute. And then to my left was all desert. On that side on my left side of the mountain was all desert. To my right was green forest and the ocean. Here, this whole area will be green, a biome that's forest biome. Okay? Here, it's all desert. Why is it desert here? Because it's dry. The air is completely dry. Why is it dried out? Because all the rain got pulled out as it went up the mountain. We call this a rain shadow effect. You obviously need warm temperatures as well. And so what you get is this happens at around 30 degrees latitude. Now we'll pull the globes are up in the windows, but when you're looking at the Earth, remember it's at a tilt. This is the equator. This is 0 degrees. This, and when I say degrees, you've all used a protractor, right? All right, so you're looking at 0 degrees. Let's say it's 30 degrees. It's at this 30 degrees where you see most of the deserts. 30 degrees north and 30 degrees south is where you see all your, most of your, not all of them, but most of your deserts. The Sahara, the deserts of the West in the United States, and most of the deserts in Africa are all going to be around 30 degrees latitude. This is called latitude. Latitude is the horizontal line. Now, what does this have to do with hurricanes? Well, let's think about this. We talked about air pressure, right? What kind of air pressure do you think is happening here? Low or high? Here, as this warm water goes up, is this low or high air pressure? Low. Low air pressure, when you look on a map and you see a bunch of lows, you see L with a circle around it. That means air is moving upwards. It's not moving down. On a high, air is moving downwards. They're relative measurements. So high pressure means that the air is moving down because, why is it falling? Because the air is Hot air does what? Goes up or down? Goes up. So if air's falling, it's higher pressure. Is air coming down or going up? Down. So high pressure is when air's coming down. Low pressure is when air's going up. When it's hot. So when it's hot,